Thank you in advance for your attention. So I'm going to talk to you about the, well, mostly, in all honesty, we're going to talk mostly about numerical methods. And we're going to talk about methods that allow us, I see the problem is not so much this, it's Rodney sitting on the corner here. All right, so let's try it like that. In order to simulate this type of thing. So I'll 2 years ago at the previous edition of this meeting, I talked quite a bit about particle latent flows. This time I thought I would focus more on liquid gas flows and atomization type problems. And specifically, we're going to talk about steps we've taken towards handling thin films in a way that's reasonably computationally efficient. So concretely, I'll lay out the methods that we've developed in order to be able to capture this type of thing. So in case you're not too familiar with this process, here we're looking at a liquid jet coming in from the left. This is an experimental image, and you can see what we call bag breakup. So this is a liquid jet that is being inflated literally by a gas flow. So there's gas getting inside this region, and you form a bag. That bag inflates and ultimately ruptures and forms a very fine spray in the process. And this is a recent simulation that we've done of this process. I should mention that all of this work has been conducted by my student Rob Chiodi, who's been working on that for a number of months. This is also quite a bit still work in progress, so hopefully you'll bear with me and acknowledge that we're still working towards getting this to be as efficient as we would like it to be. General introduction slide. We're interested in multiphase turbulence. It's important for energy system. It's important for process innovation, intensification. There's a whole range of multiphase applications that we could talk about. We'll kind of limit ourselves here to combustion type problems. So we're looking at liquid fuel being injected in a combustor. The application itself doesn't really matter. It's just a reason for us to focus on the turbulent liquid gas flow. So we're interested in the fuel spray, and if you look at an image like that, photo coming from Chris Edwards' lab from a number of years ago from a NASA-funded project, you can ask yourself a number of questions here. You know, we see the spray being formed on the left. Well, what really controls the drop size coming out of this atomization process? How do we model this predictively without any or with minimal tuning parameters? And down the road also, how do we develop techniques that allow us to control the outcome of an atomization process like this, without simply redesigning the entire nozzle, but instead maybe by introducing some external force to the system in order to tune the outcome of the atomization. So those are questions that are of interest to us. I'll do a little bit of a quick commercial for a project that we've had going on now for a couple of years, funded by the Office of Naval Research. So it's a project on multiphysics control of spray formation and dispersion. I'm not going to talk really much about that. All I'll tell you is that we've been very interested in the question of how do you modulate the flow in the nozzle, how do you add external factors like electrostatics, like acoustic forcing in order to tune the outcome of the atomization process. Of course, in order to do that, you need to be able to measure, generate the spray, measure the spray, characterize it. You need to be able to model the spray, and ultimately you need to be able to boil the data down to something that's manageable for a control algorithm. So this is a large project that involves a number of people. I'll talk briefly about, of course, the simulations that we're doing, but we'll use some data coming out of Ted Eindel's lab at Iowa State University based on X-rays so that we can see inside the spray, as well as light scattering diagnostics of the very same spray performed by Alberto Eliseda and his group at the University of Washington. So I'll start off with a brief video that was presented recently at the iClass meeting. I won't let it play entirely. I'll just use that as a way to introduce the problem. So we're looking at an air blast atomizer. It looks like this. This is running under very poor conditions, so don't worry about the big drops. This is not the conditions we're interested in. So we're spewing liquid out, in this case water, out of a central nozzle at a pretty low Reynolds number. The flow is essentially laminar. And we're interested in the atomization induced by a fast co-flowing stream of gas. So this is an annular process. The air can be swirled as well, even though we won't worry about it here. And here we'll specifically be interested in a pretty low Reynolds number for the gas stream, such that the main mode for breakup is the formation of these bags that I was mentioning. So I'll pause that right here, and we'll essentially stop the movie here. So the point of this is to show that from direct shadowgraphy imaging of the spray, you can see what's happening pretty clearly. So if you follow the left side here, you can see we're forming those bags I was mentioning. Those bags will break and burst into myriads of tiny drops and will leave behind those rim drops that are larger. This is not necessarily a particularly quantitative measurement technique. We can extract useful information from this, of course. For example, the penetration of the liquid. We can have an idea of the spray angle. We can have an idea of a lot of macroscopic information about the spray. But if we want to have quantitative information about where the liquid is, we can turn our attention to X-ray radiography. So this is something that allows us to know, on average, how much liquid do we have in terms of depth of liquid, line of sight, depth of liquid at any point in space. And then we have our simulations. And if I go back here just for a second and let it play just a little bit, you can see, hopefully, that there's some qualitative agreement between the dynamics. We have an overall flapping jet that forms bags, and ultimately things break. Okay, now if we go beyond that and look at some quantitative comparisons, well, first of all, I told you that with X-rays we can have quantitative information about liquid path lengths, so we can compare that between simulations and experiments. The simulations, here are the lines. This one here is along the center line of the jet, and then we have 3 radial locations, and we can compare that to the symbols that come from the X-ray measurements, and we have pretty good agreement. There's a little bit of a shift in the virtual origin of the jet, and we're still working a bit on curves of boundary conditions, in particular contact line physics and things like that. But overall, the agreement is pretty good. We can look at the flapping frequency of the liquid core. We're pretty much in agreement with the experiment. Where things become really problematic, so bad that I'm not even going to show you, is when we start looking at drop size distributions. And this is really what we care about. So it's all good that we match this, but ultimately, we're talking about spray. We want to get the right drop sizes. So why don't we get the right drop sizes? Well, in this specific case, it's fairly easy to understand what's going wrong. And so we're going to try to start here and try to address, or at least improve what we're doing at this stage. So a bag like this is small, as in very small. A micron is a reasonable scale for the film that's formed here. It could be even on the order of 100 nanometers. So we're looking at very small structures here. Our mesh resolution in those calculations tend to be on the order of 10 to 100 micron. Here we're actually closer to 100 micron in this calculation here. So we're orders of magnitude away from being able to get the right physics. So of course the simple answer is, well, let's refine the mesh. Yeah, but we have, again, we're orders of magnitude away, and we're not convinced that the fairly quiet process here deserves that much extra resolution. So we're going to try to go a different route. I should tell you what we're solving. We're solving incompressible isothermal equations without any phase change. So we're essentially transporting an interface. We're going to do that using a VOF scheme, and we're going to solve the incompressible Navier-Stokes with surface tension. And so I'm not going to spend too much time on that. In the interest of time, I'll just give you a summary of some of the methods we have. So first of all, we have, I call this a highly efficient structured Cartesian mesh. That means, well, we're pretty lame. We have a research code. It's a basic old school research code. So we can't do AMR with this. We don't have an unstructured capability to track the interface like Vincent will show us later in the conference. So, but the good thing is that it's efficient. It's as much as possible second order, or at least as much as we were able to make it, it's second order accurate in space and time. It's based on the pressure projection scheme with the ghost rate method. We have an inverse boundary handling of the nozzle. We have exact mass and momentum conservation everywhere. Okay. What we don't know how to do is exact kinetic energy conservation. However, as soon as we're one set away from the interface, we conserve kinetic energy. It's stable for any density ratio, and we're using a subgrid scale model to deal with turbulence. So we're already seeing this as an LES exercise. As far as the interface handling, we're using a semi-Lagrangian unsplit volume of fluid method. So it is formally second-order accurate, it's bounded, conservative. It's based on the idea that in each cell we're reconstructing the interface using a plane. Okay, so it's the old-school Plick reconstruction of Young et al. From a year later, a year after I was born. So it's been around for a while. Okay, so there's not a lot of interest in spending too much time here. What I want to say is, well, why can't we get a film? Well, it's pretty simple. The main issue that we're facing here, the main reason why we get this myriad of mesh scale droplets instead of film is because a Plick, so piecewise linear interface construction method, is pretty poor at preserving very thin structures. So numerical errors force us to break the film into droplets way too early. So what is happening is, if I have a thick film, a film that's resolved with at least a cell, potentially more, in its thickness, I can represent it using the assumption of a single interface, planar interface in each one of my cells. That's fine, this is not a problem. As soon as I go to a thinner structure, so if my film should look like this, with a characteristic size on the order or even smaller than the mesh size, then the assumption of a single plane per interface means that I need to mess up my topology. So that means that anytime we'll be dealing with thin interfacial structures, we'll be distorting them heavily because of the way Plick handles a reconstruction. Okay, so to me, that means there's work to do on this if we want to be able to look at breakup. So I'll give you a little bit of a more, potentially more convincing example of what's going on. If I put 10 cells across a drop and then put it in a flow that stretches it out into a film, and use pretty standard methods of VOF plus Plick. So again, one interface per cell and the Elvira strategy for reconstructing that interface. I'll talk more about it later. This is what happens. You spread out your drop. What you get is holes, and you're basically getting numerical noise. It's mass conserving though, but it's still, as far as representing the topology is concerned, it's pretty bad. Okay, so to me that means that if we want to do proper subgroup modeling of the breakup process, we need to work quite a bit on numerical methods such that we don't systematically incur most of our numerical errors as we get to the smallest possible structures on our mesh. The second step is, if we have the capability of representing thin structures more accurately, then we can start thinking about modeling the breakup process at the small scales. So I'll mostly talk about topic 1 here, but we'll touch briefly upon some aspects of topic 2. Okay, so I'm not going to waste any time with this. I'll directly tell you a solution. It's really the next step up in complexity that we can think of. If one interface is not enough, can we just reconstruct our interface with 2 planes in each cell? So we're going to call that R2P reconstruction with 2 planes. And so that doesn't mean we always use 2 planes. We can use up to. So we could. This method could still use a single plane. And I'm going to run a simulation of the same problem as on the left, but this time using this R2P reconstruction, where we have in blue cells that contain a single plane interface, and in red you'll see regions where we had to switch to a 2-plane representation. And that's how this looks. So you basically now maintain the sheet. So how does it work? Well, in order to efficiently tell you how this works, I need to tell you a little bit about, give you some background about how typical Plick methods work. Plick means essentially you're trying to fit a plane inside your cell that best represents your interface. Okay, and that typically means that you have 2 orientation parameters, essentially a plane normal, and then a positioning parameter, a distance. So that's a set of 3 parameters, 2 plus 1. Orientation, this is done usually by error minimization, and then 1 that's obtained by enforcing a volume conservation constraint. Okay? So that's your standard approach. Now, the way you do the error minimization for the plane orientation can vary, and there's many flavors of that. I'm going to give you 2 here. I was going to say old school, but yeah, I guess you could say it's old school at this point. In 2004, Pilliard and Puckett proposed a method that they called Elvira. There are 2 variants. There's the E-Elvira and the Elvira method. This is a very powerful method that's been very good and it's been used extensively. The idea is to orient the plane optimally by minimizing volume fraction errors in the neighborhood of the cell. So you're trying to reconstruct your plane right here, but in order to minimize to optimize the orientation of it, you're going to look at the neighborhood and see how you would have to orient your plane to get the right volume fraction of liquid in an area around your cell. Okay, so you end up minimizing an error that looks like that. Alpha here is a volume fraction. The tilde are the reconstructed variable. The non-tilde are the transported variable. So you're going to try in the neighborhood to minimize a volume fraction error. MOF is a more recent method that comes out of Los Alamos, in particular the work of Shashkov. The idea here is to minimize something different. You're going to orient your interface by minimizing errors in the phase barycenter. So you're not going to look at the volume fraction as your primary metric for orienting your interface. You're going to look at where you think your phases should be located within your cell in terms of the phase barycenters. So say that you have your green phase and your red phase, and within your cell directly you're going to optimize the location of the plane by minimizing an area like this where C is the barycenter. This is purely local. Okay, so whoop. Now, how do we do a two-plane reconstruction? Well, first of all, if we have two planes, we have now 6 parameters. So we have 4 orientation parameters, 2 location parameters. That's becoming a little tedious. We keep that reasonably simple by saying, well, first let's take a shared plane. So we're going to have a shared representation, and then we're going to start splitting into 2 different planes. And then we're going to have 2 positioning parameters. The position parameters are essentially constrained by the volume conservation. The orientation parameters, again, are coming from a minimization exercise. The minimization we do is essentially a generalization of what people have done before. We're looking at Elvira, we're looking at MOF, and we're saying, well, let's do the same. Let's just merge all this. So what are we doing? Well, we're using all the information we have available. We're going to minimize the error in a region around our cell of interest, and we're going to take into account volume fraction information, barycenter information, and we're going to add to that also a new idea that at least I haven't seen before, but I might have missed it, a surface area minimization. So we're going to say, we know already from transport how much surface area of interface we should have in each cell. Let's try to get as close as possible from that. So we have really 3 classes of data: volume information in each cell, barycenter, phase barycenter information in each cell, as well as surface area. We're going to combine all this and make use of everything together. So that ends up looking like this. The minimization is done based, like I said, on the same idea as Elvira, augmented with the same idea as MOF, plus the idea of adding a surface area error. You can think of this as a limiter on surface energy. If we have too much surface, we're just dumping lots and lots of energy into our surface, which is probably not physical. And then by tuning the weights, you can essentially get whatever you want. If you want to get Elvira out of this method, fine. You just put all your weight on this. If you want to get MOF, you put all your weight on this. So it's just a generalization of those ideas. So how does it look concretely? Well, we end up having to do minimization, nonlinear minimization in 6D space, which would suck, but it doesn't too much, because ultimately, yes, we have an optimization we need to do. We do that using a Levenberg mark card that's constrained such that volume is always conserved. But ultimately, this exercise, we want it to be minimal in the sense that we want to have such a high quality initial guess that we could almost do without the optimization. That's, to us, the only way we can really keep a reasonable cost on this optimization process. So let's talk a bit about the initial guess. So to think about how to optimally distribute 2 interfaces in a cell, here's what we've been thinking about. First of all, you can think about what you know from the transport step. You have, at the previous time step, a reconstructed interface. You transport it forward in time. Now what you have in a given cell is little chunks of surfaces. So you have information about surface area, orientation in each of your cell, and neighboring cells as well. So you have essentially p-planar elements with a given orientation and an assigned surface area. That's what gets transported into your cell. Well, we've started thinking about this as a discrete weighted directional distribution. That means we're thinking about it as something living on a unit sphere in 3D, so essentially just orientation vectors, to which a weight is assigned that corresponds to the surface area. So if at the end of the transport step, this is your directional distribution, Now you can think about, well, is the mean direction given by this information useful to me? Well, you can simply compute the mean orientation, right? You just take the average. And what you'll get is a vector that does not live on this unit sphere anymore, because you're averaging directions, so you're going to get something that has a magnitude less than 1. How much less than 1, how much lower than 1, tells you how useful this information is. So if this vector has a magnitude close to 1, then that means the reconstruction you would get from it is actually pretty good. You have a reasonable estimate of the overall orientation from this mean orientation. And for that, we just set essentially a criterion. We're saying this mean vector should be larger than a certain value. Below that, we don't trust it anymore. So let me give you an example where we wouldn't trust the mean orientation. If I add now another little chunk of interface that came in, so we end up forming a film, well, that film would be extremely poorly represented with a single interface, and you would see that directly by computing the mean orientation. The magnitude of it would be close to 0. That tells you that, yes, you can specify a mean orientation, but it's essentially a meaningless piece of information. So if this thing is below this yellow circle here, we'll say, OK, this is not useful information. The reconstruction is poor. Let's switch now to 2 interfaces. So if we have 2 interfaces, we need 2 means. For that, we need to do clustering. We're going to use a machine learning algorithm called spherical k-means clustering by Dylan and Moda from a while ago, and that gives us a systematic way of clustering those orientations such that we end up with one cluster that is, in this case, this one interface, and the other cluster, which is those 3 interfaces for which we can have a reasonable mean representation. So that's the story. With this initial guess, things are very good. The optimization exercise is fairly cheap. All right, let's demonstrate the performance of this. So this is Elvira on the left. As soon as our film, oh, so I should say that we're putting here a film in a stagnation flow. Okay, so we're just enforcing a flow field that will thin the film to very small scales. So if I show you that again, if you have the single plane treatment, things obviously break at some point. This is purely numerical breakup. There should be no breakup. If you start post-processing that and calling that, and you're studying the drop size distribution coming out of that, you're playing with numerical errors. Okay? This is the correct solution. You should be maintaining a film. And by the way, the method we have allows us to keep this film forever, essentially. We can bring it down to essentially machine 0 in thickness. So I showed you this before. I'm not going to show you again. We noticed that, so that, basically this works. It maintains a film in 3D flows. It also has a nice property. Since we limit spurious breakup like this, we end up reducing the occurrence of jetsam and flotsam, so little chunks of stuff that tend to separate. For this case, we can look systematically at the shape error and the computational cost. The shape error in this case is not a very good way of assessing so the amount of volume in our film is small, therefore the film will not influence the shape error very significantly. But still, we see that when you use this 2-plane reconstruction, we're systematically doing better, and we have just pretty much a perfect second-order convergence for the errors. The computational cost would be potentially the sticking point here. What we find is interesting. Yes, in situations where every single cell ends up requiring 2 planes, so in the coarsest situation, yes, we do end up saying that there's an increase in the computational cost. We get to on the order of 2 to 3 times higher expense for a case like that. This is a case where transport and reconstruction is all that happens. If you add a Poisson solver to this, suddenly this matters a lot less. If you go to cases that are better resolved, where you use the 2-plane reconstruction less, you in fact end up seeing some level of speed up. Okay, so we're pretty excited by this. Now, if you apply that to the case I showed you before, this Muri project that we have, where we're looking at an air blast atomization process, this is what we were seeing in the experiments. This is what we were simulating before. With this, now we're forming a film. Okay, so now we have a bag. This bag is maintained. How long is it maintained? Well, potentially forever so far. That means we have a problem. We can keep on stretching this thing forever in a way that's utterly non-physical. Okay, we have 0 thickness films that cover the entire domain, which sucks. That means that we're done with the numerics, but now we have to step back and think about physical modeling for the breakup. So I'll conclude very briefly with some notes on the modeling side of things. Okay, so there's one easy thing we should take care of first. There's a bag here, so we're inflating a balloon. There's a pressure difference between what's inside and what's on the other side. That's reasonably easy to handle in the context of a ghost fluid type method. All we need to know is that we have cells that are on one side of the film and cells that are on the other side of the film. Once we have this information, we can handle the pressure jump. So I'll talk about that in the next slide. Then we'll need to talk about how we handle breakup of the film. And that's a key subgrid modeling question. And then we'll talk briefly about film retraction. So first of all, pressure jump across the thin film. If I have a film like that, I know already how to detect it by just counting the number of interfaces I have within my cell. If I have two, I have a film. If I have a film, I need to handle the pressure jump across the film. I can create a mean film location. Since I have two interfaces, it's easy to create a shared, essentially mean film location. And across that, I can compute the curvature of this thing. And then I can compute the associated pressure jump, double it, because I'm going from gas to liquid and then liquid to gas, and then put that into the ghost fluid method, and I'm done. So we can try that. We've done that, and it works well. We can represent the pressure jump across a bubble in a sharp way, the way you would do it with the ghost fluid method for a droplet. I should say this is a thin film bubble. So both sides here are gas, and in the middle we have liquid. Okay, and the film is over an order of magnitude smaller than the mesh. Okay, so that takes care of this first little issue. This was not a particularly big challenge. Film breakup. Well, that's a bigger challenge, and honestly, we don't really have an answer yet. We're working on introducing concepts from thin film theory in order to help us predict breakup in a reasonable way. But for now, we've essentially found the simplest thing possible, which is to just say, let's rupture at 1 micron. If we can go down to 1 micron, we already have something interesting that we can test and we can play with. So you can see here a sequence of images where we're inflating the bag, and at some point we fall below 1 micron in thickness, and this thing breaks. A broken film is still not the end of the story, because now we end up with the surrounding, essentially this film ends up kind of flapping around, doing nothing useful, because again, everything that would have to happen is at the subgrid scale level. Basically, we have now broken film. We should have a rim. This rim should have a very strong surface tension force that should repel the film towards the thick rim here. So that's something we need to handle, and so that's going to be the third point. The film retraction, I'm not going to spend much time on that since I think I'm already running a little bit over time, so I'm just going to say that we've started looking at this in terms of a simple Taylor-Kulik flow. So this is the retraction of a film that ends with a rim. The only key parameter here is the Ernst-Zorch number. And for a range of Ernst-Zorch number, we can, from theory, figure out what is the expected shape. For anything related to spray atomization, you would expect to be on the order of 0.1 for the value of the Ernst-Zorch number. So you would expect to have this shape here, the thin film that ends with a thick rim. So now there's really three things that could be happening. Either we resolve everything, we have a very thick film, then there's nothing for us to model, everything should be there. We could be in a situation where the film is below the mesh resolution. Our R2P reconstruction should be good at maintaining this film, but say the rim is resolved. If the rim is resolved, then we should be good as well. So we maintain the film, and the surface tension process that brings the rim back, that retracts the rim, would be resolved. And then finally, if everything is at the subgrid level, there we need a force. We need a subgrid scale force. So we're going to just do the simplest thing right now. We're going to take the information we have from the two-plane reconstruction to create a subgrid scale surface tension force, and we're going to apply that on our resolve scale. This is naive, but we wanted to check whether this was a reasonable place to start. So we can look at this Taylor-Kulik flow. This is a fully resolved flow. It gives us a normalized retraction velocity that goes to the theoretical value. If we don't model the retraction, and put a subgrid scale film represented with our two-plane reconstruction, nothing happened. There's no retraction. We get this film that flaps around. Retraction velocity is 0. Finally, if we put in a model, we get back a rim that looks initially a little rough, but has more or less the right retraction velocity. So with this, I'll just say, oh, well, I guess I have a little demo. So for the retraction, if I pierce a bubble, it has a weird behavior. It goes towards the direction in which it's been pierced. If I pierce a bubble with the subgrid scale model, you get a maybe more realistic response or more expected response. But ultimately, what I want to show you is what happens if I simulate with two planes and the subgrid scale retraction process. Instead of showing you movies, which kind of end up obscuring things, I'll just highlight the difference here between the situation where we don't model the retraction, where we end up with this sheet kind of flapping around, to the situation where we model the retraction. The first place where we end up breaking, so this is the thickness of the film. You can see in dark red is 1 micron. So we break here first, and then right away we start repelling. The film starts pushing back, and it starts increasing in size. And what we find is some interesting stuff where we end up breaking at different locations at the same time. And so we end up forming kind of a web-like topology, leaving behind resolved ligaments, which used to be the rims that were formed in the process, which kind of looks like, at least qualitatively, looks like some of the little spider-like, spider web-like structures left behind in the breakup of the experimental bag. So this is still very early on, and there's a number of things missing. I'll point out in the next slide. But we're pretty excited. We think we're moving towards subgrid scale modeling a breakup of films, and we're pretty excited by that. In terms of perspective, one thing that's missing is the fact that we haven't been producing droplets in this retraction process. We know that there should be droplets generated. It's because we've been modeling a two-dimensional Taylor-Kulik process. We should really have been modeling a three-dimensional Taylor-Kulik process that then spews out drops. So we're working on this. And then we're not very happy with the idea of breaking up at 1 micron. It's made up. We want something that's based on physics and not on our arbitrary choices. One thing I should mention is that we're finalizing the creation of an open source library that would do that for you. We spend a lot of time working on this reconstruction strategy, so we want to help people take a little bit of a shortcut here. All right, and with this, I'll be happy to take any questions. I should mention the ONR funding as well. Thank you.